So we already have shown the amplifier circuits with MOSFET and the biasing associated with that. We started with the DC biasing. So this we have shown that the VGS value is related to VG value and also the VOV value for a given RS value, and this RS is known as degeneration resistance. Then we have also shown another kind of biasing which we also have seen in BJT in case of BJT. So I've shown this DC operation first, then I have shown this kind of biasing which is similar to the BJT biasing that I've shown in previous slides, and figure out the equations related to the same. And I solved a problem as well, which is based on this kind of biasing. So this problem showed that once we have the values, we get a relation between RG1 and RG2. So it's basically a ratio. And I also have said that generally we keep these values as high as possible. That doesn't mean that we can keep it very high. It depends on what are the commercial resistors available. If I keep it say 150 mega ohm, 1000 mega ohm, that doesn't make sense because these type of resistors are not available in the market. So generally we keep it in mega ohm, and we keep it in a range where the resistors are available in the market. So generally we keep it higher, but that doesn't mean it will be very, very high. But definitely we are not making these resistances very small because that may take a lot of power, because VDD is also connected to this part of the circuit. So lot of current will flow through this and lot of power will be consumed. This is the idea of choosing these resistors or resistance values. Now there is another biasing which is known as current source biasing. I already have shown one circuit previously based on current source biasing. I think when I was calculating the gain sometime before, which is similar to this. Okay, so and this type of circuit is known as current mirror. Okay, and what is the advantage of this type of biasing is known as current mirror. So I won't say this type of circuit, better to say this type of biasings. Okay, so why we need current source biasing? What is the advantage of the same? Now if you see this circuit where you have a current source, now the resistance associated with this current source, RCS, as shown in here, will be very high, right? This is what current source is all about. It ideally should be infinite. Now what is the advantage of this? Because it is a current source, so your this terminal is ground. So where is this resistance connected then? Between this terminal and ground. So we can put this resistance over here, this terminal and ground. Just to keep things simple, I have shifted the resistances over here. Now it is very clear that this resistance is in parallel with R0, that is output resistance. Now think about a situation where RCS is very small. If RCS is very small, it will shunt the output resistance. That means whatever current will come will flow through this. Effect of R0 will be very less. So even if your R0 is very high, ultimately the effective R0 will be very less. But if I use a current source, RCS value will be very high. Now, this is what we have seen, that the resistance associated with the current source is ideally infinite. Physically it will be very high. So in that case the effect of R0 will not be hampered that much. At least RCS will be equal to R0, so that the total resistance becomes R0 by 2. So still it is in the same order. But if RCS is very low, you'll find your output resistance has no effect in the circuit. So that is why we say that a current biasing is good. Now if you see this particular biasing or this particular circuit, there are two transistors used. And why it is called current mirror? Because we used a current biasing in this side, and the value of current, which is a biasing, right? So we need a control over the biasing. It's not like something fixed or something we do not have control over. Generally we need a control on the at least biasing, because that is where we fix our values. This IDS value is very important, because it is going to decide my GM value, beta value, everything. Okay, so what happens is, in this circuit, IDS value is related to the current flowing through this one, that is IDS1. Whatever will be the value of IDS1 will be reflected in the IDS2, just like a mirror. So you can consider here a mirror. Whatever you are fixing here will be reflected in this branch. That's why it is called current mirror. It may happen that, we will see later, it may happen that this is not exactly the same, but maybe twice, thrice. It depends on the designer, how he wants. But in general, whatever is the current here will be reflected over here. So you can fix your current here, so this current will automatically get fixed. So you have a control of current in the left hand side, and the same thing will be reflected in the right hand side. And this is our amplifying transistor. In this case, this is the amplifying transistor. Now if you look at the circuit, the gate of both the transistors are shorted, and the source and drain and gate is also shorted for the left one. So what is the value of IDS1 then? The value of IDS1 will be VDD minus whatever is the potential over here divided by R. Now these two is shorted. One thing I already have clarified, that whatever current is flowing through R will also flow through the transistor. So IDS1 is flowing through, because gate current is 0, right? So same current will flow throughout. However, if this 2 is shorted, we can say that the potential here is VGS1 plus VSS. In this case, we have made VSS is equal to 0, but in certain cases you will find VSS is not equal to 0. So somebody is putting minus 5 volt here, plus 5 volt here and minus 5 volt here. So ultimately the total voltage is 10. However, if it is not 0, then you have to consider VSS. So your IDS1 will be VDD minus VS1, that is this one, minus VSS. In this case, VSS is 0, divided by R. This is your IDS1 value. Now from this circuit, it is very clear that VGS1 is VGS2. Both are same circuit, and the ground is, both are same MOSFET, and ground is shorted, not ground, this gate is shorted, So if gate is shorted, then VGS1 is equal to VGS2, and VDS1, that is this drain source. This is drain source, right? This VDS1 is equal to VGS1 because it is also shorted. So this one is shorted, so you will find that the potential here is actually VGS1. So VDS1 is also equal to VGS1. Now from this relation, it is very much clear that if I subtract something for VGS1, your VDS1 value will be higher than this. If I subtract X from VGS1, if X is positive, then VDS1 will be greater. So this is what exactly is written. VDS1 is greater than VGS1 minus VT. This is the condition for saturation. So your M1 will always be in the saturation region. Okay, that is very clear. Now if you see from the transistor, you have IDS1 and IDS2. What will be the values of this? Beta n dash 1, beta dash n1, beta dash n2. What is beta dash? Mu1 Cox. I have said previously it is mu1 Cox. I said, and also have discussed the same thing previously. Somewhere you will find Kn dash. That is also I also have said. And what is your beta n? Beta n is beta dash W by L. Okay. So this is the relation of beta n and beta n dash. So your IDS1 will be beta n1 dash W by L1, VGS1 minus VT. Similarly, IDS2 will be beta n2 dash W by L2, VGS1 minus VT. So I kept W by L and W by L in both the cases separate. That is, this is for M1 and this is for M2, MOSFET 2. However, you know VGS1 is equal to VGS2. I already have said. So in that case, if you take a ratio of IDS2 by IDS1, these two term and these two term will get cancelled because beta n value will be same. It is a technology parameter. Mu1 Cox for any NMOS will be same for a same technology, right? So this term and this term will get cancelled because VGS1 is equal to VGS2. I already said. So this ratio IDS2 by IDS1 will be a ratio of W by L2 by W by L1. And what does that mean? If both the W by L is same, which generally are same for different transistors, which is in the same technology, then you will get both the currents are same. However, if you want this current to be twice of this current, you can just take a MOSFET which has a W by value accordingly. W by a value which is twice as the other. The ratio is twice as the other. Okay, you can choose the value accordingly so that you can control this VDS2 value. Now, the advantage of this thing is using a same control, you can bias different transistors with different value if required. Like this. Say it is another M3 you have connected in this. So if you make this W by 3, what will be the, if this is IDS3, what will be here? It will be IDS3 by, it will be W by L3 by W by L1. So you choose the value W by L as per your choice, and W by L1 is always fixed for all the circuits. So in a same circuit you can bias with different values. So this circuit will provide you the advantage of biasing different parts with different values with the same control. So maybe here it is IDS1, here it is 2 IDS1, 3 IDS1, something like that. So this biasing is important to know, and in many circuits people use this kind of biasing. Okay, so this is called your current mirror circuit. However, IDS1 value is beta n W by L1 VGS1 minus VT whole square. That is, I already have written. This is your reference. This is your reference current. This current is going to decide what is the bias in the other branches. Okay. Anyways, in this case, you have to choose a proper R value as well, because this current is will be decided by the R value as well. This is the current mirror circuit.